There's a type of graph problem that makes up more than half of all graph problems you see in coding interviews, but no one actually talks about it. And if you don't learn how to solve this type of graph problem, you're going to have a lot of trouble being successful in those interviews. When we talk about graphs, we usually see things like Dijkstra's algorithm, depth first search, breadth first search, even things like topological sort. And while these are really important, they're also very clearly defined. If you understand the algorithm, if you understand how to work with graphs, they're very easy to implement. But what happens when you don't even know that a problem is a graph problem? How do you look at a problem like finding the number of islands on a map, or seeing whether a puzzle is solvable or not, and say, yep, this is definitely a graph problem? The answer is that you have to understand implicit graphs. Implicit graphs are graphs where the graph is defined by the data itself and not explicitly defined. You're not given a series of nodes and edges, you're given some sort of data that has implicit connections. A graph is just data points that are connected in some way. And in tons of real-world scenarios, we can have data that is connected without us being explicitly told how. Here's a simple example. Imagine that you have a list of people in an apartment building and what floor they live on. You could construct a graph of this data because all these people are connected by living on the same floor. In this example, you can see that Alice is connected to Charlie because they both live on the second floor, and Bob, Fred, and Evan are all connected because they all live on the third floor. Or let's say that you're playing a game of chess. If you consider the current board position to be one data point, every possible move that you make leads to another board state that is connected to the current board. Knowing the rules of chess, we could generate a massive graph that would show every different series of moves that the game could take. Now, these are two simple examples of how graphs come up in the real world. But to reliably solve these problems in our interview, we have to be able to answer two questions. One, how do we identify when something is a graph problem? And two, once we identify it as a graph problem, how do we solve it? These are the sorts of questions that, once you really understand graphs, you can deduce the answers to these. But that doesn't make it time efficient in your interview. That's why at Byte by Byte, we really like to focus on heuristics and patterns that will help you to understand this faster. And in the case of implicit graphs, there are three patterns that you need to be familiar with: grouping problems, solvability problems, and ordering problems. In the rest of this video, I'm going to take you through these three patterns and how to apply them. And then in future videos, we'll get more into the specific code and how to actually implement these. Grouping problems are any sort of problem where we're looking at subgroups of our data. The classic example of this is the number of islands problem. In this problem, we have a grid that represents a map of land and water, and we want to determine the number of disconnected islands. In this example, you can see visually that there are two separate islands. Now, how is this a graph problem? Even though it isn't explicitly defined as a graph problem, the points of land are connected based on their location, just like the people that we looked at living on different floors of an apartment building. Therefore, we can connect the land to generate a graph like this. Once we see this as a graph, all we have to do is find all the connected components using some sort of search. You do need to be sure that you know how to do this, but this goes back to one of those core graph algorithms that you need to study anyway. So you should be familiar by the time that you get to this point with how to do that. When we do this search, we traverse through the nodes of the graph and look at which ones are connected. If you want to try this out for yourself, here are some examples of other grouping problems that you can try. I've included all the links in the blog post that goes along with this video. The second type of implicit graph problem, and probably the most common one that comes up, is solvability or pathing problems. These are basically problems that ask, what is the minimum number of steps to get to here? Or can I get from X to Y? Let's look at one of my favorite examples of this pattern, which is the sliding puzzle. In this problem, we're given a puzzle that looks like this, and we want to determine the minimum number of moves to solve the puzzle. We're allowed to move tiles horizontally and vertically into the empty space. Let's start by asking, how do we actually translate this into a graph? Well, if you think back to the chess example from earlier, you'll remember that we have our current board state, and we have a defined set of moves that we can make. That means that we can start to build out a graph that looks like this. We have our starting states, then all the states that we can get to from there, and then we can continue to build out the full set of connected states by continuing below each of these. And once we've done this, our problem becomes as simple as finding the shortest path between our start state and the solved state. In this case, because our puzzle is only one move away from solved, we can see that the shortest path is just this. Let's also look at a quick toy example so that you can see a completely different way to apply this approach. Say that we have a string and we want to find the minimum number of characters to remove so that the string is entirely made up of a single character. So in this case, AABCA would become AAA, and our answer would be 2 because we remove the B and C. Obviously, there are non-graph ways to solve this, but let's consider it from a graph perspective. In this case, our state is the string itself. And what are the adjacent states? Well, we can just try removing each character from the string. If we repeat this process, then we end up with a graph that looks something like this. And from here, we just need to find the shortest path from our starting point to any string that matches our condition of being all one character. Here's what our path might look like. In this case, you can see that our path is length 2, which is what we were looking for. Because this solvability pattern comes up so frequently, I also want to give you a general framework for how to approach it. That way, whenever you see this in an interview, regardless of the situation, you'll know how to take what you have in the interview and apply it. First, you need to clearly define the states of your data. In the case of our sliding puzzle, that was the board position, or in a chess game, that's the board position. In the case of our string example, that was the strings. The key is that we need to be able to clearly define each state and understand what the win condition is. How do we know when we found a result? In the case of our string, we can just iterate over that string and see are they all the same character or not. In the case of our sliding puzzle, we'll have to iterate over it and make sure that all of the values or all of those tiles are in order. Step 2 is to define the connections between that data. If you're playing a game like the sliding puzzle, that's the moves that you can make. In the case of our strings, that's removing one character from each position of the string. And then finally, step number 3 is to perform a search and look for that win condition. If we want to find the shortest path or the shortest distance, then you probably want to use a breadth first search. And if we just want to find all paths or any path, you can do a depth first search or breadth first search. If you know how to use this framework, it's going to open up a lot of possibilities in your interviews. Here are a couple examples of other problems that you can try that use this strategy. And again, all of these will be linked in the blog post that goes along with this video. The final pattern for our implicit graph problems is ordering. And this is basically saying, given some set of dependencies, what is a valid order of all of my data that fulfills all of those dependencies? The classic example of this is scheduling. For example, let's take a look at this course scheduling problem. In this problem, we're given a list of courses and their prerequisites, and we need to determine whether there is a valid order in which we can take these courses so that all the prerequisites are properly met. Let's start, as we have with the other problems, by translating this into a graph. We have our courses, those are the data points, and then we have our prerequisites. We can draw these in as directional edges where the course points to its prerequisite. So 0 points to nothing, 1 is going to point to 0, 2 is going to point to 0, and then 3 and 4 are both going to point to 1 and 2. Now that we have this graph, the question is, how do we find an ordering that is valid? And the answer is that we actually already have a tool for that, which is topological sort. Like with the other examples here, I don't want to get super into the weeds, but let's go quickly through how this works. To do our topological sort, we're just going to repeatedly find any nodes that don't have any dependencies and remove them as well as any edges to them. Effectively, what we're doing is saying, find a course that I can take and then take it, and then see what other courses I'm allowed to take and repeat. Here's how this works in this example. First, we're going to find that, okay, 0 doesn't have any dependencies because it's not pointing to anything else. So we remove it, and that basically becomes the first course that we take. And then we remove all of the dependencies on 0. Now we repeat the process, and we find that both 1 and 2 don't have any dependencies because they're not pointing to anything now that we remove the dependency on 1. So we can add 1 and 2 to our course ordering and remove them from our graph. Now, finally, we see that both 4 and 3 no longer have any dependencies, and so we can take those as well in whichever order we want. Now, implementing topological sort is not trivial to do, so I would definitely recommend spending some time on that, and we will be covering that in a future video. But if you know how to do it, if you know how to do topological sort, you'll be able to solve any of these problems. As with the other patterns, here are some additional problems that you can take a look at, and these are all linked to in the blog post. If you take the time to understand these implicit graph problems, it's going to totally change the way in which you solve problems in your interviews. These patterns make it really easy for you to identify these problems and then actually take that understanding of the problem and move it through to a solution. If you're looking for more strategies and algorithms that you need to know for your interview, I recommend checking out our recent video on the 8 algorithms that you need to know for your coding interview, and I look forward to seeing you in the next video.